Here we are going to look at polynomials. Our definition of a polynomial is a function that can be written in this form. This looks confusing at first, but don't let this throw you. This is just a bunch of powers of x added together, stuff like x squared, x cubed, x to the 10th, positive exponents, positive integer exponents on my x's, and then these a's are just the coefficients that go in front of the x's. This particular form is called expanded form because everything is multiplied out. Later we'll see factored form, which is actually our favorite form. This guy in front with the largest exponent, the biggest exponent on x, is called the leading term. The number, the coefficient of that leading term is called the leading coefficient. And the highest exponent we see is called the degree. So this guy here, for example, is a perfectly good polynomial. A bunch of powers of x added together. My coefficients can be anything. I can have coefficients like square root of 2 or pi, or I can have fractional coefficients. I can't have square roots of x. I can't have x's in denominators. But my coefficients can be any real numbers. This is a perfectly good polynomial. The leading coefficient is the number in front of the biggest x. That's this -4. The leading coefficient will tell us end behavior. The degree, the biggest power of x we see, is 9. Okay, this guy is not a polynomial. We're not allowed to have x's in denominators. This is what's called a rational function. That's the next topic after polynomials. Not a polynomial. This guy, not a polynomial. We can't have square roots or cube roots or absolute values of x. Just powers of x, integer, positive integer powers of x added together. Not a polynomial. Okay, this guy's a perfectly good polynomial. It's in a different form though. It's not in expanded form. It's in what we call factored form. So, what's our degree? Your first instinct is to think the degree is 4, because that's the biggest power. But no, this is not in expanded form. Imagine if we were to multiply all this out. We took x minus 1 times itself, and we took x minus 4 times itself 4 times. And we multiplied all this out. So here, I would end up with an x to the 4th times an x squared. I would end up with an x to the 6th power. This is a polynomial. The degree is not 4, it's 6. And if you don't believe me, multiply all this out by writing x minus 8 4 times, x minus 1 twice, multiply it all out. You'll get something that looks like 3x to the 6th plus a bunch of other stuff I don't care about right now. Some x to the 5th, some 4ths, and so forth. The biggest power of x in expanded form would be 6, so the degree is 6, and the leading coefficient, still this number in front, 3. Okay, this is really important. This is the heart of everything about polynomials. If you have a polynomial, p of x, and some real number c, then all 6 of these things say the same thing. If you plug in c and you get 0. That's the same thing as saying c is a solution to the equation p of x equals 0. That literally says the same thing. Both of these say when you plug in c, the whole thing equals 0. 3 and 4 are just terminology. Nothing really mathy there. A number that you plug in that makes the whole thing 0 we call a root or a 0. Those two words mean the same thing. They're completely synonymous. Sometimes we say root, sometimes we say 0. There's no difference. Now, if c makes the whole thing equal to 0, that means we found ourselves an x-intercept. The point c comma 0 will be an x-intercept. So every root, if it's a real number, gives us an x-intercept. Okay, all of that should be pretty obvious. It's number 6 here where things get different. This is for polynomials. Polynomials are special. If you have a root, c, then x minus that root is also a factor of the polynomial. That's called the factor theorem. It's pretty important. The factor theorem says, if you have a root, some number that makes the whole thing equal to 0, then you know a factor, x minus the root. Okay, we combine that together with the fundamental theorem of algebra. This is fundamental to algebra. Everything about polynomials comes back to the fundamental theorem. And in its most basic form, it says every polynomial with real coefficients has at least one root. Every polynomial has at least a root. It might be a complex number, but we have at least one root. A corollary to that says if you know the degree is n, then you're going to have n roots. A 10th degree polynomial will have 10 roots. A 9th degree polynomial will have 9 roots. A 37th degree will have 37 roots. They might be complex numbers, and they're not all distinct. Sometimes you'll have repeats in your list of roots, but you'll have n of them. Okay, we put the fundamental theorem and the factor theorem together, and what that means is every polynomial factors. Back when you were doing quadratics, sometimes you would say, oh, this guy doesn't factor. Quadratics are polynomials of degree 2, and they do. They all factor. And if it's quadratic, you'll have 2 factors. You might not be able to factor using nice, pretty whole numbers, but every polynomial factors. In fact, if the degree is n, then you'll have n factors. A 7th degree polynomial can be factored into 7 things multiplied together. They won't all be distinct. Sometimes you'll have repeats in your list of factors, but you know how many factors you're going to have, and you know how many roots you're going to have. If the degree is n, so we have some polynomial in expanded form, degree is n, then you can take that polynomial and you can factor it into n linear factors multiplied together. That leading coefficient is still going to be out front, and our factors will all be x minus a root. We have n roots, n factors. The degree tells you the number of factors, which tells you the number of roots. And the roots are whatever comes after the minus. X minus a root, x minus a root, n of those. Not necessarily distinct. You may have some repeats in your list. If the degree is n, then the polynomial has at most n x-intercepts. Complex roots don't correspond to x-intercepts. You can't graph a complex number in the real plane. And if you have repeats in your list, you can't hit the x-axis more than once at a particular point. So a 7th degree polynomial will have 7 roots, but it may not have 7 x-intercepts. It just can't have more than 7. Repeated roots don't give us extra x-intercepts. Complex roots don't give us x-intercepts. Polynomials are nice curvy, continuous functions. They turn. They change from decreasing to increasing or increasing to decreasing. Those turning points, a polynomial of degree n will only turn at most n minus 1 times. A 7th degree polynomial could possibly turn 6 times. Okay, multiplicity refers to the number of times a particular factor appears in factored form. And we call that the multiplicity of the root. If we add up all the multiplicities of all the roots, that's the same as the degree. For example, we've got this polynomial here. Perfectly good polynomial. It's in factored form. Everything is factored. x minus 3 is a factor. In fact, there are 4 factors, x minus 3, 5 that look like x plus 2, and 2 that look like x minus 8. Our leading coefficient is the number in front. It's just 7. Our degree is 11. But wait a minute, you're saying the biggest power is 5. Why isn't the degree 5? This is not in expanded form. This is in factored form. We have to imagine multiplying all this out. If I multiplied this out, I have 4 copies of x minus 3, 5 copies of x plus 2, and 2 copies of x minus 8. That's 11 factors. The number of factors is the degree. Degree is 11. What are the roots? The roots are whatever come after the minus. I've got x minus 3. 3 is a root. Instead of writing out 3 4 times, which would take a while, we just say the root is 3 and it has multiplicity 4. This root is negative 2, has multiplicity 5. And this root is 8 and it has multiplicity 2. That should be a 2. That's a typo that I fixed twice, and for some reason it's not in here. It is fixed in the version that's in Blackboard. So that's 8 with a multiplicity of 2. Okay, so the roots are whatever comes after the minus. It's this middle one that's going to mess you up. You have to think of this as x minus negative 2. Okay, notice if we add up all the multiplicities, 4 plus 5 plus 2, 9 plus 2 is 11. All the multiplicities add up to the degree. We have 11 factors, 11 roots, because I have 3 4 times, negative 2 5 times, 8 2, that's a 2 times. We won't get 11 x-intercepts though. We'll have x-intercepts at 3 0, negative 2 0, and 8 0. We would only have 3 x-intercepts. Okay, here's another example. We're in factored form. The leading coefficient's the number in front, negative 8. If we wanted the degree, we'll add up all the little powers. So I've got 5 plus 3 is 8, 9, 10, 11, 12. So our degree is 12. Add up all the little exponents. Don't let this guy right here in front throw you off. That's 5 factors of x. What number makes x 0? 0. This one's going to throw you off. You got to be careful here. So everybody will see this. We got a root of 7, a root of 5, negative 1, 9. This one in front, don't forget about that negative 8. It's not attached to this x any more than it's attached to anybody else. You could think, if you like, this is x minus 0 to the 5th. So the root here is 0 with multiplicity 5, 7 with multiplicity 3, 5 multiplicity 2, negative 1 to the first, multiplicity is 1, and 9 to the first, multiplicity is 1. If we add up all those multiplicities, 5 plus 3 plus 2 plus 1 plus 1, we get 12. Sum of all the multiplicities is the degree. Our x-intercepts here, each root gives us an x-intercept. We're not going to have 12 x-intercepts though. The x-intercepts would just be the root comma 0. 0 comma 0, 7 0, 5 0, negative 1 0, and 9 0. Okay, that is the introduction to polynomials. Our ultimate goal is to be graphing polynomials, so click on some of these other videos that are popping up to look at graphing polynomials.